I'm keeping this. Well, the getting it all.
Okay. Okay. All right. So today we're gonna start spinning through a bunch of these other slides on specific DNN accelerators. So we talked about, like, we finished off last lecture talking about like categorizing sort of the sea of early accelerators that existed, basically a bunch of processing elements at the core of all the operations is a fuse, multiply, add, and then, arranging these things in a data flow is much more efficient, right, than sort of doing it in the traditional, moving everything through the register file kind of way that GPUs do it. And so this slide deck is basically from a tutorial spun up by these authors from MIT, and Joel Emmer is like a super famous architect. Does anyone know who he is? He's actually a Purdue alumni. He's now one of the primary scientists at NVIDIA. He was an MIT professor for a long time, and then moved to NVIDIA like about a decade ago. And they sort of did this series on, partially to like inform people in the architecture community what's going on, to give like a nice overview of these DNN accelerators, and then also to sort of sell their own work. Right. So this next slide deck is really about talking about their thing, right? Their thing their paper, right, that they had at ISCO one year. So I'm going to go through this in like at some speed, and they do try to like give a holistic view of a bunch of different things that are going on in the DNN space. I will say that no individual component in these slides is like very in depth. So I am going to go through it pretty quick. Okay. And the intent of giving you guys this content is just to give you, there's a bunch of paper references in here, sort of gives you a tour de force of like the work that's going on in DNN accelerators throughout architecture. And, some of this work is also kind of in the VLSI space. Okay. So, some of this is fundamental. Some of this is just what people did for their paper. So this sort of characterization, this is what we talked about before, where you could basically have these processing elements, they're tied together, and then the way that the data moves is defined by these three different, which of these three different classes of information is staying stationary. Okay, all DNNs sort of look like this. They all have weights, they all have activations, they all have partial sums, convolution layers, fully connected layers, they all look like this. And then you can kind of characterize things by what they keep stationary. And so the folks from MIT that did this tutorial came up with what they call a different way. Okay, so instead of just keeping one flavor of the three different components stationary, let's try and maximize reuse across all three of the flavors. Okay, so not just keep one thing stationary. Let's move all of it, but keep all of it also stationary. so keep some of it stationary, keep some of each flavor stationary instead of having it, be one or the other. That's kind of the idea. And they had this mechanism that they called row stationary. And the idea is to try to maximize reuse in the register file, right? The register file is the lowest energy piece in these little PEs. You want to try to reuse data as much as possible from the RF without either moving it on the NOC or reading it in for some buffer. So how can we figure out a good way to do this? And again, the name of the game here is not necessarily raw performance, right? The name of the game is energy efficiency, which could translate into raw performance, because if you're more energy efficient, you can put down more processing elements for the same power budget. Okay, so it's not like, this work all has a flavor that is very different from like a 565 thing, right? Like a branch predictor or a prefetcher, where you're just trying to get this number of cycles to reduce. Here, we're trying to get the energy to reduce such that you can scale up the hardware such that you can get more performance. Okay, so it's sort of fundamentally different way of approaching things than we've sort of done in traditional architecture. Yeah.
Typically, when they try to go for energy efficiency, does it also reduce the space that?
Yeah. So there's two ways. There's two things you can do with more energy efficient hardware, right? So, okay. So your question is to reduce area. You reduce area simply by just having less stuff, right? If it's more energy efficient, the same amount of stuff consumes less energy. If you shrink the area, you're probably shrinking performance, right? If you've done this well. So it's not necessarily a reduction in chip area, although like you could use the extra power budget. I mean, usually what they do when they get more energy efficiency is just use it for more compute. You could, right? And in the embedded space, energy efficiency has always been a first order concern. Embedded, I mean like lower power systems, things that aren't GPUs bolted to, 500-watt power supplies, but stuff that's out in the field. So does it immediately reduce area? Not necessarily, right? Not unless you use it to do that. Other questions? Okay. All right. So they invented this thing called row stationary, or at least that's what their accelerator does. And so how does it work? Okay. So here is the basic operation. We've seen this now several times. And so the basic design of and this is called Iris, okay? There's an ISCA paper on this. Instead of only having one flavor of things sort of resident in the register file, they allow all the different flavors to stay in the register file. And they sort of stream through the weights and the input activation, and they stream out the partial sums, okay? And they do this in what's called row stationary, meaning that like one processing element is responsible for one row instead of one particular element of one of these particular flavors. So you're going to have all three flavors kind of resident, but you're only going to have flavors associated with one row of this computation resident in one PE at a time. That's sort of the shtick that is different in their thing versus other things. And so here's a simple example where we've got like essentially so let's take a 1D convolution, right? So this is a 2D thing, but let's assume we're doing a 1D convolution across each of the rows. How this would work is you'd load in 3 elements of each of, like the filter is 3 wide. So in this simple example, the whole filter sort of sits in the register file. And then I take the first 3 elements of the input map. I also sort of stream that into the register file. And then I'm producing the partial sum. Okay, as I sort of do this multiplication of of each of these elements, and then I sort of move the filter, and so I move the filter across the inputs. Benefit here is that this weight stationary is pretty good with this, right? Because the weight stays constant, but I moved across the input, so like some of the elements in my input are reused, right? Like B and C were in the register file in the first place, and they can sort of stay in the register file in the next phase to do the math as you sort of move across the filter. And then you're taking the partial sum that you created A in the last cycle, and you're sending it out potentially to another processor, because you're not done, right? If there's multiple channels here, you need to add those up to actually get the final result. So this is just a simple example. We'll see how it fits together with like a bigger network in subsequent slides. And you can continue to sort of stream these things through and keep streaming out the parts of the partial product. And that's kind of the difference in their architecture, is that they are not mapping just weights to PEs. They're not mapping just output elements to PEs. They are mapping like a row of the convolution to a PE. So the sort of overall win here, right, is to maximize the reuse across a row. You keep the filter and rows and that particular piece of the sliding window resident in the register file to minimize movement as much as you can. And if you do have to do some, iterative adding, you're also keeping the partial sum there. So it's sort of the best of both worlds, but there's not any free lunch, right? So if you do dedicate some of the space to all three of these elements, you obviously get less space for any one of them, right? So, there's going to be a trade-off here. It turns out that this trade-off is usually good, at least on the networks that they studied with their accelerator, okay? So then how do I put these things together? So I've got a bunch of processing elements. So now let's say I've got, I'm going to do this in a row-centric way. So I'm going to devote PE1 to doing row 1 of the computation. And then I'm not done, right? Because to actually get the final output, right, the final thing that's going to be, this small row here, I actually need multiple rows, right? I need to use multiple rows of the filter. I need to use multiple rows of the input activation. And I need to add all those up to actually get the final output row of the red thing, okay? And the way you do this is with that output, right? In that previous slide, I was sending the output out in this little FIFO buffer. I'm going to send the output out to another element that's responsible for another row, and it's going to take that incoming partial product and add it to the product that it's creating. And then, as you might guess, right, I need another row. So how many PEs do you think I need, given this methodology, to compute this operation here with these toy matrices? How many? What's your gut on number of PEs I'm going to need? 3? No. 5? No. 9. I need 9, right? Because I need 3 rows of the output. And each row of the output is going to need 3 rows of filter and 3 rows of the input. Okay, so to get this whole box, this whole red box, which is what I want at the end, I need 9 of these things. Okay, so then I'm just going to do it again, right? So now I'm basically, so there's reuse here, right? You can see that there's redundancy happening because obviously the rows are going to be shared across the PEs. So it's not like they're, it's perfectly mapped, or it's not like everyone is only responsible for one. You're using some of that SRAM to redundantly store the data. And again, that's a trade-off. Like, is it worth it to do this? Turns out it sometimes is. And there's also some redundancy in the rows, right? Like row 1 only exists in this sort of first column of processing elements. It doesn't exist in the second column, but 2 and 3 does, right? So you're reusing some of that data. But again, you're sort of doing this to create a different partial product. So you're flowing them through in a different configuration. And then I need to do the final thing with the final row to create, again, 3 rows of my output matrix. So the way that they sort of spatially map the inputs of their convolution to each of their processing elements is all centered on the rows of the output. Okay. And then you can observe some things here, right? Like there is filter reuse across the processing elements horizontally. So if I'm designing a network that's going to feed these processing elements, I can basically broadcast across each individual row instead of having to broadcast to everybody, right? Because I know that I'm going to, I need to basically I need to go and like stream row 1 into these, PE1, PE4, and PE7. I need to stream row 2 into PE2, 5, and 8, and so on. So I sort of create a network that is more efficiently designed to do it just to a subset of those elements. Fmaps are also shared, and there's a pattern of this sharing, right? They're shared diagonally. If you look at the diagonals, actually it's this way, right? So row 1, there's only 1 copy of, there's 2 copies of row 2, there's 3 copies of row 3, and it's sort of this triangular type pattern of where the rows are shared. So again, I can sort of orchestrate the way I connect these things in that way. And then they flow vertically in this picture. This is similar to the way other designs work, right? Where you're sort of sending the partial sum across the NOC, and then eventually it goes to the final output. Questions on this? So the mapping here gets more difficult. Right, the mapping in a weight stationary architecture is pretty straightforward, right? You just dump the weights onto each processing element in the register file, and then you stream things through, okay? Here, I need to make some decisions, and like I'm gonna have a fixed size PE array, but all of my network sizes are going to be different. So I need some kind of scheduling mechanism that will take any arbitrary convolution or any arbitrary fully connected network and then map it onto this mix of processing elements in this row-centric way. So this is only 2 dimensions, and so you can sort of like scale this up. So if we have, you've got basically a filter here where, this was a very simple example, right, where I just had that one channel in the filter. If I've got multiple F maps, having multiple F maps means what? What does that mean in the context of machine learning? There's a word for this. Batch. I'm batching, right? I've got more than one F map. So now I've got multiple F maps. I need to apply that same filter to all of those F maps. So I end up with, basically having the same weights. So I'm reusing the rows here. And then I have different F maps that I need to stream in. Okay. So basically they share the same filter row, but then they'll use different F maps. So in the processing element, when we're mapping each processing element now to a higher dimensionality than that sort of toy example where I've got a batch size and multiple inputs, now I need to say that, okay, I'm going to put row 1 from channel filter 1 in, PE element 1, and I need to concatenate both of the 2 rows, right? So the 2 rows are going to stream in through that processing element, and then I'm going to output the 2 rows that are responsible for the output. So as I sort of scale up the dimensions here, I need to scale up the work done by each PE, to account for the fact that the thing is bigger. There's reuse in the filters. So this is if I have multiple, now I have multiple filters in my design, and I'm assuming now that I just have a batch size of 1. So I have reuse of the same activations because I have to apply different filters now to the same activations. So they're actually sharing the same F-map row. And the way that this would get interleaved on a processing element is that you would sort of map just one particular row now to the PE, and then you would have to go between the 2 filters, okay? Because you'd have 2 filters that are being applied, and you're going to get this sort of p-sum that is a combination of both the p-sums that you want to get out of this, because you are now producing 2 separate outputs from these 2 filters. And then as I scale channels, which we haven't really talked about, but that was in all of the other diagrams. So now even if I just have 1 filter, I have multiple channels in that filter, I have to have also multiple channels on my activations. So here they're going to be accumulated, right, across the partial products, which means that the rows are going to be accumulated. So I need to basically interleave the channels of my of my filter and the channels of my input activation to produce that sort of aggregated row. Okay, so you can sort of keep that partial sum happening within the processing element. And so you have all of these knobs that you can play with in terms of where you map, these higher dimensional networks and how you map it onto the processing element. And this is just essentially a summary of the 3 different ways you can scale things up, and then how it affects the access stream associated with each processing element. Okay. So fine, that seems all well and good, but now I have to figure out this mapping, right? And this is a lot of the game in many of these neural net accelerators. There was a question last week on, like, is a lot of this done in hardware or in software? And a lot of this is done in software, right? There's some kind of mapper that needs to take in whatever your DNN configuration is, and then know what your hardware resources are, and then figure out how to schedule that DNN on these particular hardware resources. And, this is kind of, it's very similar to what a compiler does in some ways, right? In a modern system, you can sort of think of these mappers as sort of compilers. There are analogies to, device technology mapping. If you're doing things like on FPGAs, right? You have to actually, you place and route, you have to map the thing and place and route it, et cetera. Trying to figure out what technology your FPGA has versus what the demands of your RTL are is also this mapping problem. It's fundamentally the same kind of optimization, but it's across, different types. You have to take now as inputs to these neural networks and then have it have some knowledge of the PEs that it needs to spray it across. So yeah, so they sort of make this analogy, and they do it in the paper too, right? Like this is like classical computing, where you've got a compiler, the input to the compiler is the program, compiler knows something about the architecture, so it can generate the ISA. It knows something about the microarchitecture, so it can try to optimize things. And the compiler will use all that information to go and produce some binary program that runs on the processor. Processor gets input data, and then you get the process data out, right? That's what every program looks like. The analogy now in the DNN world with DNN acceleration is that everything becomes some kind of mapping function. So you have a bespoke like DNN accelerator. It's not represented by an ISA anymore, like your traditional processor is. It's represented by, this is the topology. Each of these things can do a MAC. This is the topology of said MACs. This is how much storage I have on each of these MACs. This is how they're connected through the memory hierarchy that I've created. Give me a good layout, right? So you basically have this mapper that is taking in as the input essentially what's coming out of PyTorch. PyTorch is, this is what an ML developer does, right? They just write it in PyTorch that will get generated into some Onyx file or something, which basically just gives you dimensions of all of the layers in your deep neural network. That is essentially the input to this mapper that says, this layer has this particular dimensions. I have this particular stride size. From that, I can deterministically say how many MACs I need to perform that operation. There's no guesswork there, as long as I'm not doing some trickery for sparsity and these kinds of things. I know exactly the computation I need. And then I also know, so the inputs to now this mapper are the data flows, implementation details in terms of how does the data flow through my DNN accelerator? Implementation details are things like, what is the memory hierarchy? How much can I store in each of these layers? Are they connected in some hierarchical way, et cetera? And then the mapper goes and spits out a mapping config, right? Sort of like how, an FPGA tool chain will basically spit out a bunch of ones and zeros that say program the FPGA in this way to represent this RTL. This mapper output says, essentially map the inputs coming in from, sort of connect the thing in this way and map the inputs onto this DNN accelerator in that particular way. And then the activations and the weights of that particular layer are the data that's coming in, analogous to the data that comes in from a CPU program. And then the output is the output activations, okay? And then there's some behavioral statistics that maybe it can take advantage of to try to, curb its mapping, right? Maybe its mapping could be smarter based on something it couldn't figure out statically. And so, and this is largely borne out to be true, right? This is kind of how most of these DNN accelerators work today. You have to have some software mapper that decides how to take the size and shape of every layer in the DNN and map it to the particular accelerator that your company wants to produce, right? This is what TPU does. This is what Cerebras does. GPUs are a little bit more flexible, but they still have some level of this, right? It's because, yes, you still have CUDA code and assembly instructions that are ultimately running, but you still need to figure out the best implementation of that code for this particular architecture and this particular network. But here it's much more explicit, right? Like this thing is like a very hardened accelerator that must, be used efficiently. And so a lot of the game is in the mapper in trying to generate efficient mappers for different sizes. And so, okay, so questions on this? Hopefully this is kind of intuitive. And yeah, so you could argue that maybe all architecture will end up going this way. If LLMs could basically answer all questions, why do I need a general purpose processor anyway? Right? Why don't I just build DNN accelerators and no one will ever code anymore and I'll just ask the LLMs and this is what we'll do for the rest of our lives is figure out how to map LLMs onto Mac units. I don't know. Maybe, maybe not, but there's certainly a significant amount of this in the field. And, some of you will go off and get jobs doing this, no doubt. Okay, so this row stationary thing. So remember, this is created by these MIT folks that are trying to push their secret sauce. So why do I care about any of this? So they basically mapped out the different ways that you could place the data on, their array, which is essentially the same as other processing element arrays that are out there. And they showed the relative energy efficiency. So all of these have the same number of MACs because if it's the same layer, the number of MACs is equal. And how much energy are they spending in data movement, which is basically the rest of it for each of the MACs. And you can see the different options, right? So weight stationary, you spend a lot of time, you spend a lot of energy moving the activations around. You don't spend a lot of time moving the weights because it's weight stationary. You have to read them in once and that's it. And then you spend a lot of energy moving around the sums. There's two different types of output stationary that we covered, both of which kind of give you the same type of pattern. You spend more energy moving the weights, but less energy moving the outputs. Actually, there's three flavors of output stationary. OSC, I don't remember what that one was. That one's even worse, but we're moving the activations. And then, of course, there's that thing, which is row stationary, which is RS. And, no individual component is less than any of the other individual components, but they've traded off, the energy movement. So like you spend more energy moving weights in row stationary than you did in weight stationary, but you spend far less energy moving activations around because now there's activation locality, right? Because you're keeping those in the register file. And that's how they sort of got a win. Interesting here is they didn't compare this with input stationary, right? Where blue should have been low, but that's what's in the paper. So overall, this thing sort of beat the other ways you map stuff to the processing elements. Questions on this? All right. What else did they do? So this is their iris. So this is the paper that they proposed, and they actually taped this out. Part of the reason I think people like this paper so much was that they did like an actual tape out, which isn't always true at architecture, where sometimes we just do things in simulation. You can argue whether that's worthwhile. Like, do you actually have to spend all the time to do a tape out to get a paper? They did, so it sort of gave them additional credibility on their energy numbers. And this was the overall flow of what they did tape out. So again, once you're dealing with a real system, you have to have a finite number of processing elements. In their case, it was like 14 by 12. They had a finite global SRAM buffer, and then they have basically streaming queues that allow you to stream in the weights, the input activations. And then they have specialized ReLU that's sort of dealing with the outputs as it streams back out to the off-chip RAM, right? And they hooked this up to a system and it worked. So there's different ways so the game in the mapper is basically trying to figure out the right way to deliver each of the different types of things that we need in DNNs. So, if you've just got sort of this sort of multicast knock, and that's what they had created, then you could basically use any delivery pattern, right? And then the delivery pattern you chose to use would be optimal for whatever you wanted. So here's some examples of what they did. So here's their physical PE array. This is what they actually have taped out. So it's a 14 by 12 number of processing elements. And then they looked at AlexNet. This is kind of an old paper. You can sort of give them a pass. Like, I know everyone's like, oh, AlexNet, nobody cares. But, it was sort of what everyone was using at the time and a reasonable proxy for what was useful. So if you sort of looked at the configurations of layer 3 to 5 and how they would map them to their processing elements, they would basically they would replicate the weights right across each of the rows of their processing element. And they had 13 as the dimension in the y-axis. So they were able to use almost all of their physical processing elements when they mapped this layer to the array, but not all of it, right? This is a problem when you have this sort of fixed spatial architecture. If it doesn't perfectly map, then you end up with like noise on the edges, right? This is also true for your CUDA kernels. When you launch the CUDA kernel and you've got a bunch of extra threads, you have a bunch of threads that are just checking the if condition and exiting, right? That's kind of the equivalent here. It doesn't match perfectly. And, there's no way to sort of get around that unless you start doing complicated things like trying to pack other stuff into this empty space, but then that makes it more complicated. And so then how do they deal with stuff that wouldn't just fit? Okay, so this was nice because it sort of fit within their physical array based on the storage that they had. If layer 2, for example, was bigger, so it had 5 in the y dimension, 5. So they needed 5 rows for the weights in the y dimension. So they replicated that, but you can only do it 2 times. And then the x dimension was bigger than their PE array. So now you have to basically cut it up to get it all on there at the same time, right? So you had to cut up that 27 and then just spray a 14 across, the first 5 and then spray 13 across the next 5. And so you can imagine the kind of Tetris games you have to play here, right? That's essentially what the mapper is doing. It's trying to figure out like how to hack this such that I'm not wasting elements, but that I still can orchestrate the communication I need for my for my neural net. And this is completely dependent on whatever the layer shape is. Okay, so you have to take in the layer shape to determine these mappings. All right, questions on this? Again, I don't expect you to understand the gory details. None of it is particularly interesting. You know, I mean, it's kind of interesting, I guess, but it's, you know, it's sort of the most logical way you could do this, right? Like, how do you logically map these things? There wasn't a lot of magic in that. So another thing that these guys did was trying to estimate performance. So as you know from 565 and even this class, like a lot of times in hardware, we have like cycle level simulators to try to simulate the behavior of programs that, you know, that could do anything, right? These programs can't do anything, so we probably don't need a cycle level simulator that's at that level of detail. We could probably do this more back of the envelope, okay, and do it quickly. Because cycle level simulators, the problem is it's slow, right? Like, even if you run the simulator for like 3 days, you're going to get maybe a microsecond of actual time that, you know, passes, because machines are way faster than a simulator. So what if I want to just, you know, I've got my DNN workloads, they have these topologies, and then I know what my accelerator looks like. I want to be able to like play games, right? I want to be able to like explore the design space of like, what if I stretch it this way or this way? Like, how does it affect performance without having to spend time in a cycle level simulation? So is there sort of a good way to do this? And they developed a methodology to do this. This was another one of their papers called iExam. So this is, you know, this is like good advice for building a thesis, right? Just kind of name everything with the same like first 3 letters, right? So the iris, iExam, go to your thesis, you can call it, I don't know, eyes or something, right? So anyway, so this, I guess you could argue that it also sort of deblinds you, because now it's like, oh, it's the iris guys. This thing is called iExam. Or maybe it's somebody pretending to be you. Anyway, so they did this with roofline analysis. Who's heard of roofline analysis? Some people, did you cover this in any other class? Maybe. Did I cover it in this class yet?
565 and 666.
Did they cover roofline?
Was in the book.
It's in the book. Okay, so you read the book, no one else did. You're shaming your fellow classmates. So roofline is in that book because Patterson's written the book, and Patterson, the student, like proposed this. Okay, probably just haven't updated the slides to, you know, reflect everything that's in the book. So what is roofline? It's meant to be kind of a high level estimate of maximum performance. Okay, so I'm not going to worry about like peculiarities of like what's happening on each cycle. What I really want to know is how many max can I get per cycle? That is my parallelism. Okay, so I have a bunch of Mac units. If they're all always doing something every cycle, then I'm good, right? I've hit the peak performance of this part. And so that represents, and you know, what the game is to try to be high on the y-axis, like every other graph you've ever seen, right? Now, there's going to be some physical limitation in terms of how many PEs you can actually put on the chip. So that determines the like theoretical peak performance of your chip. This is the number that's on the back of the box for the GPU and the CPU that says it's this many flops. It's just like, if I can keep these things busy every cycle, this is what it would give me. Okay. Now, you never actually get that. You get some fraction of that. And the way that roofline tries to you know, contextualize that is the x-axis, which is the number of max you need per data that you read. So you can think about it like, if I go to the right on the y-axis, my workload is getting more compute intensive, right? I need to do more work on every piece of data that I read from memory. If I go to the left on the x-axis, then, you know, that's a crappy workload for a giant machine, because that means that I need to do very little work for every piece of data that I load. So that basically the compute intensity, and there's different ways to, you know, this isn't the only way to do roofline. It could be, you know, generally the x-axis is data intensity. How you choose to represent that data intensity is usually dependent on the program. For neural net accelerators, it's max, because that's all they're doing. Okay, so it's max per data. You think about this as like, you know, floating point. It's sort of like the compute intensity we did for the CUDA programs, right? Like how many floating point operations were there per byte of data you read? Okay, that's what this represents. So going to the right means your program has a lot of compute. Going to the left means that your program doesn't have a lot of compute. And then you've got this slope, okay, that exists before you sort of, so, you know, if you have, there's this magic line here, right? This dotted line where the workload itself has enough compute per data to, in theory, hit the, so in theory, the machine now is limiting your performance, not anything else, because like the workload itself actually has enough max data. It's been optimized enough, there's enough max per memory read that in theory, you could get all the way up there. If the workload is below this dotted line on the x-axis, what do you think that means? Not you, you already know what this means. So the dotted line is magic, right? Because it says that like the workload theoretically has enough compute per data to satisfy the machine. What happens if I'm to the left of that dotted line? Less reuse. Okay, so then what's going to limit me?
The workload is memory bound.
It's going to be memory bound, right? And that's what this slope sort of is. This is your memory bandwidth, right? So if you, as you go to the right of this line, this dotted line on the x-axis, your workload needs, so much data per Mac that you can't keep the Macs busy. Okay, and then you end up, you end up basically being limited by your memory bandwidth. So if I'm a lowly program all the way over here, like very close to the origin on the x-axis, then that means I load a whole lot of data for every Mac. And then I am get my peak performance in terms of Macs is going to be limited by how much data I can feed in, which is your memory bandwidth. Okay, and then as the compute intensity of the program gets better, I'm bound by my memory here. And then as it gets better, my peak performance goes up, right? I'm still saturating memory bandwidth as I'm on this slope line. And then as soon as I get to this roof line, the very top, and I start crossing this way, I'm no longer saturating memory bandwidth, I'm saturating compute bandwidth. That's the idea, okay? And then every workload is going to have some point in here that's not necessarily like perfectly on any of these theoretical lines. And the way that this paper proposes, to estimate the performance of DNN accelerators is to like add varying levels of realism to the system, right? Like, there are storage hierarchies that actually have higher bandwidth than the main memory bandwidth. So then you have to take that into account. There are, the sort of different microarchitectural pieces will move what your potential roof line is based on what your program is doing. And so that's how they sort of approach this. So yeah, so the bandwidth bound, you're essentially bandwidth bound if you're in this region because you're basically limited. Your workload doesn't have enough work per compute to saturate the compute units. Once magic boundary, you're now compute bounded because you sort of are using the PEs and your workload has enough compute in it. Now, there are theoretical lines above what you actually built, right? And so this is how they do their performance estimate. So step number one is take a look at the maximum work parallelism in the workload. So this could actually be below the number of PEs if you have a giant chip. But in theory, like if you think about a CUDA program where you're launching 10 million threads or something, like there's a lot more parallelism in the program than you can actually get out of the SMs that you've got. And so that is true for the DNNs as well, DNN accelerators. So you start out with like, all right, high in the sky, what is the max parallelism I have? And then you try and bring it down, to some level of realism by looking at the max data flow parallelism you have. So now you have to take into account the way that that data flows through, because there's going to be dependencies that need to be satisfied. So it's going to get a little bit less. Then they just sort of keep doing this, right? So then they go step 3, the number of active PEs under finite PE array size, meaning that you're not going to be able to perfectly pack your PEs, right? Because you're going to have like these situations where you've got empty space. And that means that that's going to limit the number of active PEs you can have. And again, you need to take in the dimensions of both the array and the layer to figure out what step 3 does. And then step 4 is the number of active PEs under, right. So finite PE array size. So that's just accounting for the number of PEs. And then finite PE dimensions is like accounting for the fact that I have to do this chopping sometimes, that I have leftovers. And then they do it again for the number of actually fixed storage, because each of these things has only a finite amount of register files. So that means I can only put so much on it at a time. So they account for that, and your sort of peak performance starts to get lower and lower. And then they have additional iterations where they sort of account for the fact that there's insufficient bandwidth. in the average bandwidth is insufficient, meaning that like, you can look at peak bandwidth, but that's not the whole story. Like any program, there's going to be peaks and troughs. And if the average bandwidth is insufficient, then it's going to lower your roof line even further. And then they can take a look at, or at least where you are on the current roof line, right? And then they can take a look at what happens if I don't have enough instruction bandwidth, like to actually feed these things the next instructions, because they do have to feed them like what are you going to do each cycle with what data. And that sort of lowers it additionally. So I think that the sort of key takeaway here is that, hopefully you understand at least what, roofline is attempting to do. And that if you can sort of take averages across these sort of broad specifications, you can try and make the roofline much more refined. And so the red thing represents, the fixed number of PEs you actually get out of this layer, right? Because it's like, I have to account for the shape, I have to account for the storage of the PEs, and then everything after the red line, the last two steps are about the difference between the average bandwidths and the actual peak bandwidths that again take you further down to what you actually end up getting out of the thing. And you can do this without a step-by-step cycle simulation, right? You could do this with back of the envelopes based on what the mapper is going to do and based on your assumption of the rates and speeds and feeds of each of your networks. So you could do this with a spreadsheet, basically, without the need to do like, okay, on this cycle, I'm going to execute this instruction, and then this is this cache miss. Like, you don't need to do that. There's no variability in the workload once you've got it mapped. You can do this with a simple set of linear equations. It turns out it works out pretty well. All right, so here's an example of how they do this, right? So, they have a bunch of input activations that are flowing in. This is a common configuration. This is going to be weight stationary. So showing this for weight stationary, coming across all of the, sort of downwards across the row like we've seen. And then, of course, when you try to map the actual layer, you can't use all of the processing elements. So only a subset of them are going to be used. So that decreases the maximum potential. Right. So then you can look at, so why would I do this, right? Why do I want this high level estimate? I want this high level estimate because I want to decide how to build the DNN accelerator. This is before the thing is built, right? Like, this is like an architect. I want to figure out what I should do so I could potentially change things like the configurations of the networks. Okay. Like, for example, I could, configure the PEs such that I have like a unicast to every PE for the weight, and then a broadcast for every PE for the inputs, right? Or I can have these sort of interleaved multicasts. Like I can play games with the way I've connected these PEs, and I can account for that in my spreadsheet model to try to like affect the bandwidth and tell me what the performance is going to be for a given layer dimension. And so anyway, the first iteration of their Iris thing, like use basically a broadcast network to share data to the PEs. This is good because it's high reuse, right? So you're broadcasting the same data on the same pins, but it's relatively low bandwidth because I can only send that same data. I can't send different. A unicast network, there's no reuse because now you're sending separate signals from each of the sources, but there's high bandwidth. And then of course, the sort of network that everyone wants is the last one, which is like all to all. So I have complete configurability, which is essentially what a crossbar gives you, but like that sucks because it's hard to scale. Power, energy consumption goes down. If I tried to build like a giant PE array with everything connected by a crossbar, it's going to be way worse than a GPU. So then why did I even bother, right? So they try to you can sort of play these design games on like, well, where might I need a crossbar? Or where might I want to do unicast versus multicast? And then, this slide deck just goes on to basically describe mesh networks, which if you've taken 666, you should know there's routers, right? And you can sort of route things in different places. And, if you've read, did they make you read Bill Daly's paper in 666? Route packets, not wires.
Yeah,
Yes, you talked about it at least, right? So for a long time in networking, the whole game was VLSI, right? Like I'm going to route wires on my design, and I'm going to say that I'm going to, send this particular, I'm going to send stuff that goes from this thing in my network to this thing, and I'm going to harden that when I build the chip. And then Bill Daly came along and said, this is stupid, right? Like, why am I doing this? I'm handcuffing myself to this particular configuration. Let's just make the thing programmable essentially by having routers, and then just have packets flow the information through those routers. And then I can have a very flexible topology based on, routing packets instead of routing the wires, right? So now the thing that you used to do statically in the VLSI world no, don't do that anymore. Just give me a simple static design that then I can program. It's funny because now architectures are kind of going back to right? Because like programmability causes inefficiencies. So, there's this constant push and pull back and forth. So anyway, if you've got a sort of mesh-based router network, then you can configure it to do, many of these different topologies. And they did this in their follow-on paper. So that's why it's in the slide deck. Right. They've got a hierarchical mesh. There's really not much interesting here, except that, okay, so this is the first paper they did, right? V1 on the left-hand side. In the second paper, they had a 2D mesh to connect these things, so they had more configurability, so it made it better. There's some data that says it's better, right? So it's 7 times better speed up and 3 times better energy efficiency. And they also added a bunch of stuff that's sparsity. Okay, so a summary from what I want you to get out of these 70 slides is hopefully an understanding of the taxonomy of the different ways we can map things, an appreciation that, there is a space here on how we map DNN layers to accelerators. I'm actually working on developing like a follow-on, like 1 credit class to this class that sort of goes into this a bit more deeply than I'm able to, because I don't know, teaching you guys all of the GPU stuff and then all of the DNN accelerator stuff all in one class is kind of too much given how much DNN accelerators have exploded. So yeah, those who are graduating, it's not going to come, but it might maybe in a year or two once I cobble it together, I'll try to have something like that. But I want you to sort of have an appreciation that this is kind of a whole space, and this is what the folks at MIT did, and they did a nice job disseminating this and kind of making it accessible to give you a tutorial on how this works. Now so they have a bunch of slide sets. The next 4 are all sort of targeted at different ways to additionally run DNNs, the different kind of funky things people are doing to try to run DNNs. I'm going to run through them, relatively quickly. Again, like this one, feel free to stop me if you want. But again, the purpose of this is not to go into the depths of every particular example that are in these slides, but to just give you a flavor of the space with the last lectures that we're going to cover on this. Questions on this before I move on? All right. Okay. So co-design. So this is kind of a word that some people think is a dirty word. Some people think is like a mantra, right? So co-design is like, I am going to change the model and change the hardware to hopefully make everyone's life better, right? So in the ideal case, I change the model gets more accurate, and I change the hardware, and the hardware gets more efficient. Good, right? And in the sort of villain's case, I sacrifice one for the other and say, I've only sacrificed a little bit over here and I don't care about that, which happens, right? Like, oh, it's only like 0.5% less accurate. I don't know. I don't know how we're supposed to interpret that, right? But anyway, co-design at its core could be like a symbiotic activity. A shining example of this is sparsity, right? So there's this guy, Song Han from MIT. He was a Field Valley's student at Stanford, who's now a professor at MIT. He sort of came up with this pruning idea, right? That like there's a bunch of zeros, you can prune the zeros, and you can actually make the network better. The accuracy of the network gets better because it doesn't overfit as much because you're dropping weights, and it makes it easier to accelerate because now it's more sparse. So if I do special things in the hardware, it actually runs faster. So that's like a symbiotic win, right? Where I've changed the learning such that it adapts to the nature of the workload. So there's a lot of sparsity in here, and I can actually prune weights. But I can make the hardware much more efficient than in the dense case because I know there's all these zeros here, okay? So that's kind of like the ideal case. And then there's all these sort of perverse trade-offs along the way of like, I'm going to take away this. Like maybe both things don't get better. Both things don't get better all the time. All right, so what are some examples of co-design? Reducing precisions, okay? When you reduce precision, you change the problem. You change. Like as architects, typically, if you take 565, you can think about GPUs also play with precision now, but typically we run a program and like that's the program. The programmer wanted FP32, the programmer wanted FP64, we just gave it to them, right? That doesn't happen so much anymore. Even in GPUs, they are playing with the precision. There are things called, who's heard of the transformer engines in a GPU? Maybe some folks. The idea behind this is that the neural net programmer doesn't actually know what precision they want, right? Because the precision they need may change as they sort of flow through the network, right? Because maybe I need 16 bits here, maybe I need 4, maybe I need integer, maybe I need floating point. And again, that's based on a dynamic range of the data, right? Like how big do I actually need to represent if I had like a big representation? And so I can't statically say, as somebody cranking out PyTorch, that I definitely want this level of precision. So the idea is to sort of take that away from the programmer and leave that to the system. Let the system decide what precision you need based on how it's observing the data. And that's essentially the idea behind NVIDIA's transformer engines, which are basically just things in software that then make use of these low precision tensor cores that try to analyze, this is the data that's flowing through the neural net right now. I can resize it to be actually smaller as it goes to the next layer because I don't need that big a representation. And now my next layer gets faster because I load less data and I do less math, right? And then sometimes, if it's too small, then you can make it bigger because you think that, I should be making it bigger now because, it looks like I'm coming out of the range. And all the end developer cares about is like, how long does it take to converge, right? That's all they care about. They don't care about like, what is the specific value right? They just care about, well, they do care if it's right, but the rightness is in the accuracy, which is just basically like how accurate is it and how much does it converge. So system designers have sort of exploited this, even in conventional GPUs and definitely in these bespoke accelerators to play games with the precision. Okay, so you don't need FP32, you don't even need FP16. In a lot of cases, you just need, int 4 or int 8, and it still works reasonably well. So some ways we can do this, there's some very simple ways, like just take floating point and change it to fixed point, right? So floating point, you all know, IEEE 754 sort of allows for these very large, small numbers. Fixed point is, if you took the 362, you know what fixed point is. Hopefully everyone, has some of that in their background where we sort of assume that there's a point. I have 8 bits and I assume that there's a point somewhere in those 8 bits. Everything to the right of the 8 bits is going to be, let's see. Everything to the left of the 8 bits is going to be, 2 to the 0, 2 to the 1, 2 to the 2. Everything to the right of the 8 bits is going to be 2 to the -1, 2 to the negative. And you can only represent some numbers, right, in this format. Like you can represent half perfectly, but like it's hard to represent things where you don't have the right, power to reciprocal. And that's fixed point. And so some of these work perfectly well with fixed point. So you could sort of just take your floating point, smash it down to fixed point, and potentially change the bit width. Fixed point hardware is also way simpler, right? Floating point hardware is complicated. You have to do mantissa compare mantisses, do shifting, do adding, do rounding. Like this actually takes a lot of hardware. If you look at the size of an FPU, it's much bigger than the size of a fixed point unit because it has to maintain this IEEE 754 standard. So you can gain a lot by just going to fixed. Then even if you are doing floating point or doing fixed point, you can just reduce the width of the precision. So going from 64 to 32 to 8 to 4. And then you can do nonlinear quantization on top of that. And so, okay, so that's one approach, reduce the size. The other approach is to reduce the size of each operation and the compute needed for each operation. And the other is to reduce the sheer number of operations or the sheer number of values that you need to store. So sparsity is sort of an example of this, right? Like pruning the network, taking out weights, compacting the network, so compressing it if there's redundant values, or in particular, if there's values near 0 or 0 values, or just exploit statistical similarity in the activations, right? If there are patterns that repeat, then I can compress those, and I can then be much more efficient in the number of operations and the storage required for those operations. So all of this broadly falls under co-design because I am fundamentally changing the program. And there are many different approaches to this. The overall objective is to basically reduce the size, improve the speed, and improve the energy efficiency while still preserving accuracy. Okay, ideally the same or better. And then it's kind of an open question of like how much we can play with accuracy and still have people want to use these things. I don't know the answer to that. So anyway, so if we look at costs, so why do we do this? So if we look at the sort of relative energy cost, so remember we looked at some of these big numbers before, right? So the 32-byte DRAM read is going to cost you 640 picojoules, which is a huge amount of energy. So if we got rid of those by capturing locality, we get 2 orders of magnitude like goodness in our processor. But there's still room, right? Because if I'm doing a 32-bit floating point multiply, that's about 3.7 picojoules worth of energy. Whereas if I can smash that down to an 8-bit add, it's 0.08. picojoules of energy. So I gave myself 2 orders of magnitude when I went from, reading from DRAM every time to capturing locality. If I can live with 8-bit adds instead of 32 floating point, or I can't do adds. So I guess the fair comparison for the mult and the mult is the 8-bit mult. I can give myself another essentially order of magnitude by smashing down the precision and smashing down the complexity. And then there's the area wins as well. So the area, and this is big because every millimeter square of area that you save is now more processing elements you can put down. So that helps improve performance. So if I look at the size, and these are all like actual taped out numbers, right, in real technologies. This is by a guy named Mark Horowitz, who's a professor at Stanford. This data is fairly old, but still the rates still hold true today, even on modern technologies. Your 32-bit floating point mult is going to be about 7,000 micrometers squared in the particular technology that they're studying. And if I can bring that down to an 8-bit mult, again, you've got an order of magnitude reduction in the size, which in theory is an order of magnitude increase in compute for the same area budget. Okay, so shrinking things is good, and it's good like in a big way. So that's why you see a lot of these things doing it. Number representations. This again, hopefully this is review, right? There's a bunch of different ways you can represent numbers. You have to cut them up into mantisses if you're doing the IEEE floating point standard. Otherwise, there's sort of, this is 200 level stuff, hopefully. Fixed point, floating point. Again, you guys should know this. There's this funky thing called dynamic floating point or dynamic fixed point. Okay, so they don't go full on. You don't go full on floating point where the mantissa sort of is allowed to float, but you are allowed to change where the decimal point is based on the nature of the data. So it's sort of like I start out with the decimal point here where I've got 7 minus f minus bits for the integer fraction part, and then just 3 bits. So let me just give you the actual numbers, right? So you've got 5 bits for the integer part and then 3 bits for the fractional part, and then I can reconfigure the thing to instead interpret this as as this other number where I've got well, it's not 7 bits because you have a signed bit there if it's a signed fixed point, where I basically have all fractional bits, right? So you could on the fly sort of change where the fixed point is, right? And that can give you some benefit without having to go to the full-on extent of what IEEE 754 floating point says, right? Like IEEE 754 floating point is called this weird name because they had to come up with a standard of how to represent numbers non-exactly. There are infinite different ways we can represent numbers non-exactly, right? It's just that the IEEE was the standard, and that's how floating point got designed. But now that this is super important, people are coming up with all different funky ways of representing numbers inexactly. And dynamic fixed point is sort of one thing that's been, taken a look at. So you can sort of vary where the fraction based on the layer to try to get increased, to not kill accuracy, but get increased performance. And so here's some numbers, right? So whenever you do this, if you ever try to publish a paper on this, you have to say, what did I do to accuracy? If I change the data type of the network, how did it affect how well that network predicted what it was trying to predict? So, this is a table from one of these such papers where it was taking a look at trying to reduce the precision from 32-bit floating point. So this column that says 32-bit floating point baseline, this is like as good as the network did. I think this is top 1%, top 5%. I don't know what it is. Does it say? Yeah, top 1% or top 1. Sorry, top 1. So what does top 1 mean in machine learning research? What does it mean when I say top 1? What do you think?
The highest probability prediction.
The highest probability prediction. So when you run something through a neural net, it doesn't literally say cat, right? You basically get a vector, right, that has values on it that says how much I think it's each of these things, right? Is it cat, dog, whatever. Top 1 is I take the highest one, the one that this is what matters, right? This is what GPT is going to spit out to you. Doesn't matter what the top 5 really is. It just means what are I going to actually give the person? So top 1 says how often is that one that is the highest correct? Okay. There's another metric called top 5, which is much more loose. Was it sort of in the top 5? Which, you'll get better accuracy as a number, but is it actually practical? Which of the top 5? I don't know. So it's top one. So top one is the one that really matters the most, and that's what this is plotting. So they took a look at a bunch of different networks, and then they sort of smashed down the bit widths in different layers of that network. Okay, so they took the layer input. So like, for example, in LINET, the baseline is 32-bit everything. And then they took the layer outputs and then smashed them down to 4 bits. They took the convolution parameters, so the filter values, and they smashed them down to 4 bits. They took the fully connected parameters and they smashed them down to 4 bits. And they got 99% accuracy as opposed to 99.1% accuracy. Seems like a win. I mean, I guess, right? Like will you notice? And it's way more efficient to do it this way. Yeah, I don't know. I don't really know the right way to interpret this. I think that systems people would say that this is fine. Machine learning people, sometimes they sweat for like 0.1%, right? Like I just spent 40 days on 100 GPUs to get this 0.2%, and you're just gonna like take it away. I don't know. So again, the jury's still out on like how much this is okay, but from a like high level, like ballpark perspective, like this is pretty good, right? It's still mostly working. It doesn't work as well as it did, but it worked most of the time. And I guess, you know, in the big scheme of things, if the energy and performance win is enough, this is okay, right? You can sort of live with it. Because 99.1, like, it's still not perfect, right? So you're living with the 0.9 already. Can you live with 1 instead of 0.9? Probably. Okay. So anyway, and then they did this for a bunch of different networks, changing the bit widths in various different ways. And, you know, the accuracy does drop. It never gets better in this experiment. It's possible it gets better. Right? That's the crazy thing about machine learning, is that maybe the training can like gloss over this and you run it for a few more epochs and it actually got better. Yeah, but it usually doesn't. It usually gets worse because you're losing information fundamentally when you reduce the bit. Okay. And you can do a bunch of tricks in the network to try to help yourself. So if you normalize things, then it naturally reduces the range, right? So like you may, if you have the raw output of just like sending this activation through these filters may produce values all over the place, or like with a wide range in certain places. But then if I apply a normalization layer, remember that batch normalization layer we talked about a long time ago, it attempts to try to bring all of the values closer together, which will reduce the total range of the data. So if you add, so you know, this is why it's co-designed, because if I add a normalization layer, then I know that my data values will be closer together. So then I can reduce the precision for the next layer, right? Because I know that the values are sort of smaller, right? So if I kind of center these things, I only need values close to 0 as opposed to needing values that, you know, are sort of, I need many more bits to represent, right? 0 is golden, right? Because I need like 1 bit to represent 0, right? I just need 0. And then if I set these small deviations, the actual magnitudes, and the differentiation between those magnitudes become less important. And this is obviously, these are old slides, right? They've sort of like drank this Kool-Aid full on, right? This was in 2016 when they were like, oh, you know, everything used to be floating point 32. And so they went to floating point 16. This was pre-tensor cores, okay? So they had, you know, specialized Mac units in the Pascal card that, you know, it natively supported FP16 instead of FP32. And then the next generation was the Volta, where they had the tensor cores, where they only supported FP16. And then they went to, you know, Ampere, where they supported FP8 and FP16. And now they're into, you know, if you look at Blackwell, right, it's INT4, right, is what the tensor cores support. Because why not? And then we also had to drop the F from flops, because it's not a fl anymore. It's a t, because it's a tensor up. Because I can get a bigger number with a T than with an FL, so now everything is tops, okay? So don't be fooled, right? It's not like magic happened. You just shrunk the size of the thing we need to do, so we need a quarter of the hardware to do it. Yeah, so so this was a trend. This is obviously a trend that was highly successful, which continued. TPUs do the same thing. You know, their shtick, you know, who went to Jeff Dean's talk? Okay, did anyone notice anything about his talk? Interesting. I noticed one thing that was interesting. I know there were some interesting things, but like one thing that struck me about his talk.
Was it the CPU V1, V2?
Yeah, he talked about the TPUs, right? So TPU, there was a V1. I think this is 16-ish timeframe with V1. They've done multiple iterations of the thing. You know, now it does training and inference. But Jeff Dean did not say the word GPU once in his talk. Okay, when he was talking about CPU, he was talking about TPUs and how great they were, and he was like, "They are like 100 times more efficient than CPUs." Next slide. So you know, so for the same reason that all these data flow accelerators can be better, you know, in theory in energy than GPUs, the TPU is the same kind of thing. It's like the TPU is like a practical manifestation of a DNN specific accelerator on steroids. Okay, Google has put billions into making their own hardware so that they don't have to pay NVIDIA trillions for GPUs. They still do, not trillions, but they have a whole fleet of GPUs and a whole fleet of TPUs, right? Which is why it's kind of funny that he didn't even mention the word GPU. Because it's actually kind of a pain in the butt to do this yourself, right? Like you have to now maintain the whole software stack. You have to make sure that your technology is even, you know, your fab technology is keeping ahead of NVIDIA, otherwise it's not worth it. Right now you're in the dog eat dog hardware game and it's a lot harder to keep up. But they do, and they have a whole engineering division, and you know, it at least seems like it's a net win for them. Because they still do it. They still roll new TPUs. But you still can't buy a TPU, right? Like I can't buy a TPU and like plug it into my lab machine. They sell it as a service, right? That I guess that's Google's model. They don't want to deal with distribution supply chains and having physical things on trucks. Like I'll just give you an internet connection. You can log into my server. Maybe that's more efficient. I don't know. But anyway, so TPU does the same thing. They reduce the precision, right? And they've been playing the same game that GPUs have been playing to try to keep up. Because what do you do, right? And as long as everyone is okay with 0.1%, then, you know, we'll just do it that way. Okay. Brainwave, right? Microsoft doing a similar thing, and everyone's coming up with their own funky representations. So MSFP9, so Microsoft floating point 9. I think there was like an NVIDIA int for something too, right? Like some weird way of like twisting the way the data is represented because it's easier to build the hardware for that particular company. You know, this is kind of like an easy win, right? To sort of propose a new representation that you can hyper optimize in some way, right? And companies have done this. And you know, the key thing here is that they're getting smaller and there's less information in them. And then all the differentiation between the different types is like, okay, well, what information are we keeping? Trying to keep the right information in those bits is sort of the game in type, you know, creation. I don't find this particularly interesting, but it is a thing, okay? Trying to find better ways to represent small bit with data. Right, okay, so this is just sort of the precisions you need. Bit with scaling, yeah, so these are just a bunch of different academic works, right, that have also tried to take advantage of, you know, shrinking bits, et cetera. Binary neural nets, like, why do I need any more than one bit, right? I mean, that's next, right? That's where we're at. You know, come take this class in 2 years and like, that's where we'll be. And then, you know, so then but like right now it sucks, right? Like accuracy lost 19% on AlexNet, like they can't get the training right on that lower precision at this point, yeah. Or at least at the point of these slides, yeah.
There was a 1.5 bit paper that came out a couple of months ago.
Okay.
That showed a very high accuracy on LLM.
Okay. And LLMs may change the game too, right? Because like every time the network topology changes, I mean, look, if you've got like 1 trillion or tens of trillions of parameters, do you really need 32 bits for all those damn things? Like maybe the more parameters we give it, this like the more tolerant it will be to the smaller bit sizes. So like there's good reason to believe that it will get smaller and they'll figure out a way to train these things. But you'll have a ton more parameters. Like, is it a net win, right? If their size just, you know, that's the kind of trade-offs that we'll be in the next 5 years. And then after that, I don't know what's how are these things going to continue to scale? I don't know, right? Like there's only so many tricks we can play. There's only, when you're down to 1 bit, right? It's like when you shrink transistors, like when you're down to a couple atoms, you're gonna split the atom to transmit a signal. Like there's only so far you can go. So we're gonna have to find different ways to do this, which is kind of the interesting part. Maybe different bizarre architectures, etc. But right now, these kind of single bit things do not work particularly well, at least at the time of this publication. Maybe they work better for transformers, right? And CNNs, maybe not so much. Right, you can do funky things with XORs, right? Like once you start getting down to like single bit precisions, you can sort of do these crazy operations. But again, like the accuracy loss is there, which is, and this is on AlexNet too, which nobody cares about. So, you know, it's easy to evaluate this in academia, which is why, you know, a lot of these papers did evaluate AlexNet. Ternary, so let's, instead of 2, let's try 3, right? You know, not bad accuracy loss on AlexNet anyway. And then you can train these things and quantize these things in intelligent ways. So like, this is a whole field of CVPR and ICLR papers, is like trying to figure out how to do this better and well. Beyond this we get into here. And then of course, if I do have that low precision, architects can be like, all right, let's go build a machine for it, right? And let's go get a hardware paper on like an actual machine. And, you know, and that's the other nice thing, I guess, about this field is that it's easy enough to tape something out here, because like I can't tape out a processor that's going to compete with an Intel processor or a GPU. Like it's just too damn hard, right? There's just too much in the stack. There's not a lot in this stack. All right. It's max connected together. That's it, right? I can tape this out and, you know, I can be somewhat competitive from an energy perspective with like real chips being taped out by real companies, which is kind of different than the way things have been in the past, where everything you taped out was a complete joke versus, you know, something that 5-7 nanometers that Intel or NVIDIA was going to produce. Okay. What is this? Quantization, right? So you're trying to figure this out. I sort of covered this a little bit, and this is just a whole slew of data on the effects of this. Okay, that's it for this slide set. I probably will look for a post in Piazza, but what I might do is not have a lecture next week and post a video of me going over the final exam or the exam from last year with the solutions by the end of the week. Give you guys some time to finish off your coursework, study for the exam. In fact, do the final exam on the Tuesday of the last week of April, and then have one final class to just cover the last of this, have a kumbaya goodbye, and then be done for the semester. I'll hold office hours next week, and I will post a video of like reviewing the final exam to try and give you guys like some context of that, because I know you need to prepare for it. Any questions on this? All right, good. Thank you. And I will see you guys in person, I guess, for the final exam next, not this coming Tuesday, but the Tuesday after. If you can't make it to office hours and you want to come chat with me about the midterm or whatever, just send me an email. I'll try and work something out. Okay. All right, that's it. I'm done. Have a good week.